My name is Ricardo Menotti. Hello, everyone. I'm an associate professor at the Federal University of São Carlos in São Paulo, Brazil. I would like to start by thanking Susana Martin for the material and attention provided. This will be a short version of her 2-hour workshop, which I highly recommend for those who have interest in FPGAs. I used to be a hardware guy for many years using hardware description languages like Verilog and VHDL. I love doing this, but I admit that the learning curve is not easy for students, and moreover, projects are more and more complex. So I decided to adopt high-level synthesis tools that are already quite mature today. And one API came in good time, so I'm learning this new methodology. Let's omit the first part of the tutorial since Praveen already gave us an excellent introduction to one API yesterday and other presentations today. So our focus will be the development cycle for FPGAs. And let's learn some of the most common optimization used with FPGAs. It is worth mentioning that this is a development cycle using high-level synthesis, which consists of automatically generating hardware from software programs. The classic cycle would take much longer to be understood, even with simple examples. As I said, let's keep the basic part for DPC++. Before completing the labs, let's talk a little bit about FPGAs and how to use them. This high-level synthesis methodology is much simpler than the traditional one, and let's see why. I kept only 3 slides of the basic part to explain the main difference between CPU, GPU, and FPGAs. While the software model distributes the code to run on different cores using parallel for construct, the hardware model builds a data path in which data flows in each iteration. So it's very different how the code maps to CPU, GPU. It explores the parallelism in a multi-core, multi-thread, SIMD pipelined way, both on CPU and GPU. And on FPGAs, we built a custom pipeline. We can also do multi-core, but it's not a common approach, as we can see next. So let's do a brief introduction about FPGAs. The acronym is Field-Programmable Gate Array, which means programmable hardware. Gates refers to logic gates like AND, OR, XOR, NOT, implemented with transistors. Array means there are many of them on the chip. By many, I mean billions today. Field programmable means that the connection between them and the internal components are programmable after the deployment. So the research area is commonly referred to as reconfigurable computing. Let's see how FPGAs do this. The first kind of blocks we have on FPGAs are small building blocks of logic. Names vary by manufacturer. Logic block or logic element or configurable logic block, adaptive logic model, etc. are some of them. The building blocks are you choose how you configure them and how you connect them determine what function the FPGA performs. This is usually not explicitly chosen, not even when using hardware description language. You only describe how the circuit should behave or how it is composed of smaller parts, and the synthesis tools is responsible for generating it for you. Basic blocks are based, these configurable blocks are based on lookup tables. Let me add here a little explanation about them. This is important as it is the basis for reconfiguring the FPGAs. These usually answer the main question about reconfigurable hardware. That is, how can we change its behavior? So inside a lookup table, we have this kind of structure. This is a 2 inputs LUT or lookup table. And we have multiplexers. The inputs are the controls of the multiplexers. And we have input bits here, reconfigurable input bits. So to change the logic function here, we can just write the right bits here, and depending on the input here, we have the correct output of the function. So this is the secret of the FPGAs. We also have internal blocks of memory that can be accessed with very low latency. This is not what we call device memory in cycle model. It's part of the memory model. We need to explicitly instantiate them or pass some parameter to buffer accessor to have access to these memories. And we also have DSP blocks, which means digital signal processing blocks. Some mathematical functions such as addition and multiplication are available in dedicated hardware blocks, and compilers are able to infer and instantiate these blocks instead of building operations using conventional logic with the logic elements that I just mentioned. And these logic elements are connected, and the routing circuits are also configurable. So the blocks are connected with them and determined by your code. Again, this is not explicitly described in the code. You describe the behavior of the circuit, and the synthesis tools generates all this for you. FPGAs have been available since the 1980s. At the first, they were used in isolation, which made it difficult to put an interior system there. More recently, they have come to be used as accelerators. Since then, you can profile your code, find the critical sections or bottlenecks, and write a kernel for them. Then you accelerate functions. These accelerated functions run on a PCI attached to the FPGA card. The host interface, it's also baked in to the FPGA design on the board. In this portion of the design is pre-built and not depending on your source code. And this consumes a considerable part of the chip, as we will see later, and also explain part of the long delay in synthesis of the hardware. No matter how simple your kernel is, it needs to communicate with the host. So that's why it's sometimes it's a long compilation time. Here we have two FPGA boards used as accelerators. Here we have network interfaces, high-speed network interfaces. There are many network applications taking advantage of FPGAs because they are critical. Area is a mid-range product with just over 1 million logic elements. Strategic is a high-end device, high-performance device with almost 3 million logic elements. The communication with the host, it's also different. And here we have memories external to the chip and the board, and they are used as memory of the device memory. And some could say, I'm happy with my CPUs and GPUs. And in fact, they are very good. But FPGAs can lead to very, very good speedups for some kinds of workloads. Here are some of them. And not all applications will take advantage of FPGAs, but some of them will give you really, really good results. And let's do here I want to give you a general idea of how the code is turned into hardware. So when we are coding for FPGAs, we must remember that the code will not be executed one instruction after another. There is a compilation step, but after that, it is a hardware synthesis process. So the hardware is composed by computation elements like arithmetic operations, memory loads and stores to fetch data and write back, and control and scheduling operations. These are control path signals to synchronize operations. The pipeline has some fixed latency operation clustered together in a basic block, and we have handshake signals for variable latency paths like ready, done signals in each, things like that. Here's the main difference compared to processors. If we were to compile this code for a processor, it would become something like load E, load B, add, store C, and etc. One of another. In hardware, the computation is done spatially. So we have simultaneous hardware to increase the performance. This is very massive parallel because we can instantiate independent operations and do that at the same time. And the limit is the amount of hardware we have, and nowadays we have a lot of hardware available. Well, it's important to note that this communication and automatic data transfer is very complex to be implemented manually. Maybe that's why high-level synthesis is gaining so much attention lately, because we just have to write the software and put some directives or pragmas, and the compiler will generate the whole stuff under the code. So also we have load and store units to on-chip memory, and to access local memory inside the chip and the global memory that is on the FPGA board. How can we extract parallelism from this kind of hardware? We do operations in pipeline. So it's a common way of implementing hardware SQL kernels on FPGAs using single task kernels. They containing another loop that was not present on parallel 4, because the parallel 4 is correspond to this other loop, and the work executing multiple stages. That's why it's called the pipeline parallelism. And we need to have this in consideration when he writes the code. I will show you some concerns about that. So the key concept is that built-in dependency make FPGA powerful for many algorithms. For instance, here we have an accumulator, and we can compiler is able to identify and create a specific data path to do that. And every we have one loop iteration for each SQL clock here on this example. So we don't have a parallel 4, we have a single task running, but each clock cycle starts a new iteration that is very fast, even with slow clock compared to CPU and GPU. And how do I use a task and still get data parallelism? We can improve this pipelines unrolling some loops. So we replicate the hardware structures and do that in parallel. And the unrolled loops still get pipelined. So we have three iterations starting in one cycle, and then another cycle we have another 3 iterations starting, and the previous one will be on stage 2 and so on. And we also have task parallelism. This is an example of multiple kernels, and they can run in parallel. You can run more than one kernel at a time, and this is an available example on DevCloud, on Base Toolkit, and we can use pipes to exchange information without sending to information back to memory, reading and writing, reading again. So this is a interesting feature to custom hardware. So we can build these ND range kernels, yes, but no problem. But tasks usually imply more optimal pipeline structures. The best way to implement custom hardware is with single task kernels. So let's see the steps before the lab. I will explain the steps, and after we can do this together. The FPGA development flow starts with emulation. So we write data parallel C code, compiles for the emulation, and checks if the code is functional, right? The second step is the optimization report or generation. And here we can identify bottlenecks and see some improvements. And after then, we can compile it to FPGAs, which implies a long compiler time, hours, to get code ready to run on FPGA. So basically, here we have compilation steps, and here we have a compilation plus hardware synthesis to generate the bit stream for FPGA, which is the FPGA configuration bits. The command is composed by the compiler, of course, and the target platform files that you want to compile, link options, and specific FPGA arguments. Emulation answers me this question: does my code give me the correct answers? This seems to be the minimum required of a compiler, but in hardware things can get complicated. To have efficient hardware, you need to do several things in parallel. If you evaluate delays a single cycle, the operation will be performed at these previous values and will generate wrong results. So the manual methodology, it's very, very complicated to get the functional version. And so this is the flow. We compile the code and run on a CPU. And we have a explicit selection of emulation device. We can pass an argument to the compiler, and we put this if-def on the code to select the right device selector, which is an FPGA selector or FPGA emulator selector. So to emulate, you use the parameter. Okay, my code is functional, right? And now we need to optimize and find for bottlenecks and etc. This is done by compiling with some other parameters. Sorry for that. Basically, this FSQL link will generate the report. The default value is early. When you put image here, you will have the FPGA image, the long compile. So the default is the report, just the report, and not the FPGA image. Then if you're happy with the reports, with the results, you can generate the bit stream. So when you compile it to FPGA, it's possible to generate profiler-enabled code to work with VTune, like Vladimir just explained. I think the Intel analyzer is not compatible with FPGAs, and it's also possible to compile the FPGA devices separately and linking to avoid the unnecessary compilations. You can separate the files because this parameter will generate the bit string with the long compile, so you can partition your code to avoid recompiling host-only code. Here are some reference and resources about FPGAs on one API. And now you're going to the first lab, the FPGA development flow. I will introduce the tools, and this is the agenda. I will mention the reports, loop optimizations, memory optimizations, and after the first lab, we will do the second one with this application, a Hough transform kernel. And if you have time, I can talk about other optimizations techniques. Just explaining the steps here. HTML report is a static report showing optimization, area, and architectural information. It's static because it's a HTML, but it's very dynamic, as you will see. You can click parts of the hardware and get information. It's very, very interesting. And it is automatically generated with the object file at this .prj / reports. And we have a throughput analysis. It's about the initiation interval and maximum frequency. And we also have area analysis, how much space your code allocates in the device. We have a nice graph viewer of the hardware, which is very useful. And we also have a schedule viewer to see operations of the hardware along the time, along the clock cycles. And we have a memory viewer, and as I just said, it's possible to generate the code with profiling capabilities, which will insert counters and profiling logics in your hardware to report this after on VTune. That's how you collect profiling data with this command, and you can import in the VTune after. I did not try this again, but I'm planning to do this in a near future. So, kinds of optimizations compiler are able to do. Some of them will be done automatically. Others we need to help the compiler. So a little review. We have single work item kernels, which are more common, and parallel kernels. For FPGAs, the compiler will automatically detect the kind of kernel, and loop analysis, most loop optimization, and most optimized FPGA kernel are only applied to single work item kernels. So that's why we prefer to implement single task constructs. So single work items kernels are written like this. We have a lambda. This part of the code will turn on hardware, and the range kernels are possible to generate hardware also, but are more limited. Let's understand what initiation interval means, because this is important for optimization in FPGAs. Suppose we have this kind of code, and we have the iteration number here. So the hardware will start the first iteration loading the operators. Then the addition operation will be done on the second step, but the second iteration just started in pipeline, and the store operation will be done while another plus operation, add operation, and another pair of loads will be made in parallel. So this is the best case we have. Sometimes things goes wrong. So the Intel high-level synthesis compiler are able to apply some loop pipelining techniques to reach this best case objective, because sometimes we have dependencies between operations, and the solution must wait the finish of the first iteration before start the new operation. And compiler can do improvements on this by loop pipeline techniques, but sometimes we need to help. Sometimes you must wait more than one clock cycle. The one clock cycle is the best scenario, but sometimes dependencies can't resolve fast enough, and also you can have an intermediate scenario like six cycles or things like that, which is still good. Why could this happen? We have a lot of reasons. One of them are memory dependencies. For instance, this accumulators array are retrieved from global memory, and this means many cycles to access it. And we can see this, do these optimizations later. We can ignore vector dependencies, showing to the compiler, I know I'm doing here. This is because E and B are pointers. The compiler assumes that data between them can overlap. If you put this directive here. The compiler will ignore the dependency, but you are the responsible to ensure that data does not overlap between them, of course. Other reasons, maybe we can have data dependency intra iterations. This to finish this code, this iteration, we need to complete the previous one. So this is a data dependence. And we have lots of things we can do to improve. Change it to a simple calculation, or pre-calculate operations on the host and transfer them to the device, and much more. So we also mentioned the looping and rolling stuff, and the frequency is if Fmax is the max frequency of working on FPGA. Maybe a slow operation can slow, maybe not. Your interior kernel will work at the lowering frequency of your circuit. So if you have a piece of hardware that runs slow, your interior kernel will be slow. So the compiler risks to sacrifice clock frequency to get a higher initiation interval, but sometimes you can adjust this with parameters. Here we have an example. If we unroll this loop 8 times, we have a short operation that will be done in cascade. So this will be a long critical path, and this will increase the latency, the signal propagation, the electrical signal propagation path. So it's better to reduce the number of rolling, or put a intermediate value here, because this can increase the latency, but not the initiation interval. So it could be a good idea. So here we have some more things we can suggest to the compiler, suggesting an initiation interval, or saving area on the device, and etc. So the memory model on FPGAs is a little bit different. As we saw, we have a global memory external to the chip, and inside the FPGAs we have a local memory or private memory that are the same for single kernels, and we have low latency to local and private memories, but we need much cycles, clock cycles, to access the global memory, external memory. So what to do? We can declare local memories, transfer data to local memories, process locally, and then write it back to global memory. It's an option to do that. Even with local memory, sometimes we have access bottlenecks, and we need the arbiter. This can stall, and it's not desired. So we can do optimizations to improve this. Also, which is banking memories. We have something like the DDR memories that we can implement on FPGAs, and we can replicate the data to avoid the concurrency on access. we also can improve the quality on access to access more widely words instead of accessing 4 bytes. We 32 bits. We can access 128 bits each cycle. This is another improvement that we can do, dividing memory into independent pieces. Here we have to rewrite our code in the parts that are related to the start access, but sometimes we need to do that. So here we have some example of attributes for memory optimization, and here we have how the pipes works. We have multiple kernels, and we can read data from global memory. It transfers data between kernels to save time, communication time, instead of writing back to the global memory and reading again. This is how the code looks like. I can write in one pipe in one kernel and read from another one. Let's go to the labs. Let's see, we have some 20 minutes to do that. So let me take a look on the Slack channel. Oh, everything is okay. I put some instruction to get the tutorial files there. So we have 4 labs here, but let's skip the first 2. Lab 0 is about Jupyter notebooks. Lab 1 is about DPC++ basics, which was already covered. So the lab 2 is it's about the FPGA development flow. There are detailed instructions here. You can repeat this slowly afterwards. Here are the same informations, and basically we can write the code here. If you want to change the code, you must run the cell to overwrite the file, and here are the commands to compile and run the FPGA emulation code. This is what we mentioned about the compiler parameter and choosing the right FPGA emulator selector here. Basically, this is a array sum, and the code that will becomes harder, it's here. This is the fork that do the sum. And here we have the results. The first step is basically to emulate and see if the result is right. The second step is to generate reports. Here we have the same code again, in case you want to change the first one to test. And here we have the commands to generate the report. It's about 1 or 2 minutes to complete. The instructions here are for accessing the report direct here on Jupyter notebooks, but for some reason they are not working. So we will download it and open locally. Yeah, it's done. I think I already did this before, but here we have the lab on the bin, simple for FPGA reports. Here we can have an idea of how much code was generated. Let's see, for instance, the system file, it's more than 2,000 lines of system verilog, and this file, it's an XML file. Here we can see the IP cores instantiated to accomplish that task. We have lots of IP cores here, and here we have the report. That's I already zipped the folder and transferred it to my machine. It's here. Let's see if it's open here in another tab. Yes, this is the report. We have a summary here. We have a throughput analysis here about the loop. We have area analysis here. As you can see, we have 21% of the logic elements, 18% of the memory allocated to the static partition, which is the board interface, the communication with the host. And even the kernel system, which have 1% of the device, a considerable part of the resources are used to communicate with the memory, the global memory interconnect, because the memory, it's a DDR memory, and we need some protocol to access it, so controller, and the system itself, it's here. Let's see. We have the second lab. Let's go back to the second one. The second lab, it's the Hough transform lab. We have a PDF here with the instructions, thanks to Susanna. And here we have the commands used to compile the example. Let's see if the PDF loads. Okay. Basically, this is a computer vision application, and this code transforms a pixels in line volts. The input are a monochrome image with black or white pixels, and sometimes it's interesting to convert this on a set of lines. So the classical representation, it's not good, and this is the used representation here. Basically, we have a pair to represent a line, pronounced rho and theta. Rho is the distance from orange, and theta is the angle. For each pixel of the image, we have a number of lines varying the theta, and we must sum the line candidates, summarizing the pixels which intercept the line. So here is the kernel code. We have a pixel array, which is the image. We have the accumulators for for each line, and basically we perform the image on X and Y coordinates, and if a pixel is white, we will increment every line which intercepts this pixel. So okay, so let's go to the compilation step. Let's copy this command here and go to the labs, lab 3, original. Here we have the first step, the emulation step, and then the report step. The emulation step was concluded. We have a verification in the code. Let's see the code while the report is generated. Here we have the code. So the kernel is here. And basically this is the first version. And I have the report here for this first version. Let me see. It's one. Which one? This one is the original one. So we have a long delay between iterations. We have a long initiation interval. It's so much cycles between iterations. This is because we have memory access here. We have the exact line here. So we can change it and optimize this. The way we will do that will be, let's see the solutions here, because we have 5 minutes. You can do this later, but the solution is, the first one is to use local memories here. So you can do a diff checker after, but basically we declare the local accumulators here, and we initialize them, and we act on we store the increment on local accumulator, and outside the loop we transfer to the global memory. This is the first optimization proposed for this lab. This will improve this initiation interval to 1, around 1. Okay. Here is the line, modified line. The second improvement is to unroll the loop to increase the parallelism, and for doing that we will just put this programmer here to unroll 32 times. This will replicate the generated hardware to do this in parallel. And we also put this directive here to ignore dependencies on the arrays. And the results are seen here, but we have an issue with this because the iterations need to access the same memory bank, and an arbiter was generated. So the last step is to banking memory, and this is a more complicated one. because we have to declare the local memory in two dimensions. The last one is the number of banks I'm using. So this is the directive according the second dimension. And we have to modify the code a little bit to rearrange data on this two-dimensional way. But it's just in the initialization of the data and the final transfer to the global memory. Here we have almost the same code, and the result is better. We don't see that red spots here that are bottlenecks on memory access. This is the indication. As I said, this is a static report, very dynamic, because it's possible to click on parts of the hardware and see the related code. It's very interesting. Well, I have the compiled versions here for FPGAs to prepared for another course, and here we have the files, and if we tried to run here, we will have no success because we don't have an FPGA node right here. So we need to ask for a node with this capability, FPGA runtime on DevCloud, and if we have some of them available, we open an interactivity session, and now we can see that this node have an FPGA or two attached here, okay? And we can run the code, and you can see the difference between versions, among versions, but we have some segmentation fault error here. Probably the system has been updated since I compiled this code, and I could recompile because it was hours to compile which one. But anyway, the execution time remains the same. I have a chart here to compare the execution time. It was impressive. It's in Portuguese, sorry, but it's just for the versions and the execution time is here. And we have some graphs here. It's interesting to see that here we have a log scale, so it's very, very impressive, the speed up. And we have some resources comparison. We have very different numbers here because we have little or almost 10, 20 DSP blocks and lots of register and logic utilization. But if we put the normal scale here, we can see whether the variation in resources like registers and logic utilization, but we can see the DSP blocks. That's it. So we have no time to questions, I think, but I'm happy to answer it on the Slack channel.